Picture the last aircraft you flew on. Whether it was for a holiday or business trip, it probably looked something like this. With its low-mounted, swept wings, cylindrical fuselage, conventional tail design and underslung engines, the modern-day airliner has been a staple of our skies since the mid-1950s. When Boeing first launched their hugely influential Dash 80 model, the predecessor of the 707, in the summer of 1954, its design was so iconic and groundbreaking that externally very little has changed over the 70-year period since its introduction. And perhaps even more incredibly, a mere 5 years before its introduction, Boeing was still making aircraft like the Stratocruiser, emphasizing the revolutionary design changes that took place over this short period. Although we have made incredible advancements such as wingtips, composite materials, and, more recently, sustainable aviation fuel, these developments haven't led to fundamental design changes. However, stricter environmental regulations and an increased focus on sustainability and efficiency might force a bold departure from the conventional aircraft design that has served us for nearly 70 years.
In this video, I'll showcase 3 aircraft of my own design, each of which I've taken through the initial aircraft design process, and I've linked a detailed report in the description for anyone who'd like more information on this process. These 3 aircraft are my own interpretation of where the future of commercial aviation could be heading.
With sleek, glider-like wings, the truss-braced wing concept maximises aspect ratio, lowering induced drag and improving efficiency. The blended wing body looks to come straight from science fiction, merging the fuselage and wing into one seamless aerodynamic body. Or could the future take the form of the logic-defying supersonic oblique wing, with its pivoting wing providing efficient flight in both the subsonic and supersonic regimes, potentially returning passengers to the world of supersonic flight? The idea of using a support to increase a wing's length and thus aspect ratio is not a new one. In 1953, Maurice Hurel's HD-31 first took flight, proving to be a great success. Boasting an improved range over its competitors, its ill-timed entrance to the market competing with faster jet airliners of the time was the only thing that stopped its widespread adoption. To understand why we might want a higher aspect ratio, let's consider 2 wings, both with the same area. The wing with the greater span has a greater aspect ratio. Drag can be broken down into 2 main components, parasitic and induced drag. A larger span, and thus larger aspect ratio, leads to a smaller induced drag. It's the reason why gliders have such long and slender wings, and why there has been a recent trend to increase airliners' aspect ratios.
During design of this aircraft, I deliberately forced a high aspect ratio of around 15. This yielded a higher lift-to-drag ratio, improving takeoff and landing distances and cruising efficiency. In fact, Boeing actually predict a 10% fuel burn reduction due to the increased aspect ratio alone. But as with anything in aircraft design, there really is no such thing as a free lunch. The reduced sectional area of the wings would mean fuel has to be stored elsewhere, and airport wingspan restrictions might force the implementation of some form of folding mechanism, adding to the difficulty of an already complex manufacturing process.
Boeing do still seem keen on this idea, and, if all goes to plan, we could expect to see their X-66 concept take flight in 2028, potentially ushering in a new era of aircraft design and efficiency.
It would be remiss of me to talk about the future of aircraft design without mentioning the blended wing body. A seamless transition between fuselage and wing produces an aerodynamically efficient body with a significantly reduced wetted area and thus a reduced drag.
On paper, the possible benefits of a blended wing design look almost too good to be true. A 27% lower fuel burn and a 20% higher lift-to-drag ratio are examples of some of these benefits. The essence of the blended wing is a central body made of thick airfoil sections housing passenger bays, gradually merging into a conventional wing. This formulaic layout lends itself to entire families of aircraft, capable of fulfilling different missions. From short-distance regional flights to long-range intercontinental flights, the arrangements of the bays within the centre body can be varied, offering airliners the possibility of easily outfitting their entire fleet with different blended wing configurations. Airfoil selection can be carefully tailored to provide an elliptical lift distribution along the body, span loading the aircraft and producing a far lighter structure, as the wing does not need to support the extra weight of a fuselage. Exciting new technologies such as boundary layer ingestion or distributed propulsion could be used to power this aircraft, potentially improving upon the outlined benefits.
However, the blended wing does still face some issues. For one, manufacturing the non-cylindrical pressurised cabin could prove to be difficult, although recent developments in composite materials could help this cause. Then there's the lack of established design methodology, with aircraft designers having to build from the ground up new design methods. This would exponentially increase the development time of such aircraft.
Despite this, Boeing's X-48 scale test aircraft has shown great promise during its testing and development, suggesting that with continued research efforts, blended wing bodies could revolutionise commercial aviation.
Symmetry in aerodynamics is often seen as a fundamental rule, a principle so ingrained in aerodynamic design that it would seem counterintuitive to challenge it. But what if breaking this rule could unlock new possibilities, like maybe a return to supersonic flight?
A variable sweep wing is a combination of a standard wing and a highly swept delta wing, with the regular wing offering the best subsonic performance and the delta wing excelling at supersonic speeds. Iconic aircraft such as the F-14 and the Tornado both use this technology, but it doesn't come without its challenges. Turning the wing requires a heavy pivot mechanism capable of withstanding the strenuous structural loads placed on the wings. A pioneering NASA scientist, Robert T. Jones, found a solution to this problem, namely the oblique wing. This is an ingenious design whereby the entire wing pivots around a single point, creating an asymmetric but aerodynamically efficient shape. The oblique wing also satisfies the area rule, a key principle for minimising drag in supersonic flight, by ensuring that the aircraft's cross-sectional area changes smoothly along its length. The fact that one wing is forward and the other is aft means that the sectional area is better distributed along the aircraft's length.
But despite its promise, supersonic flight with any wing configuration still faces considerable challenges. The pivot, no matter how refined, still adds weight to the aircraft. Couple this with the fact that supersonic aircraft require a much greater fuel weight, and, at least in my case, you end up with an aircraft that weighs nearly twice that of its counterparts. Also, an often overlooked concern, in my opinion, is that of passenger perception. A wing that seemingly defies all conventional logic might not inspire confidence in its passengers, potentially leading to a reduced number of ticket sales despite its speed advantage.
The oblique wing is perhaps the most unconventional of my three designs. It challenges our fundamental understanding of aerodynamics, but if we can look past its strange appearance, it might just hold the key to making supersonic travel viable once again. As we venture further into the future of aviation, the possibilities are as boundless as they are exciting. Circular wings, twin fuselages and box wings are just some of the aircraft designs that I didn't get to cover in this video. The future of flight isn't just about refinement, it's about reimagining the very essence of how we soar through the skies.